Okay, here we are. Hello, guys. My name is Hunter, and I will be teaching you guys today about heat capacity as taught in Chem 105. And so let's get started. So as you may know, as you may remember, heat capacity is defined as the amount of energy needed to raise the temperature of an object by 1 degree Celsius. So this could be like, I don't know, say a cell phone by 1 degree Celsius, like the capacity of a cell phone, the capacity of a stuffed animal, a bow tie, something like that. So yes, so an example of this could be like, if you put out in the sun a metal spoon versus a wooden spoon. Let me see something real quick. Okay, cool. So if you put, why am I not showing that? Okay. Okay, so putting a metal spoon versus a wooden spoon in the sun. So like if you put just like any object in the sun and compare the like heat capacity of them, what will happen is that they will eventually start heating up, and you'll notice a fair amount of difference of like which one is hotter. So for example, the wooden spoon will feel a lot colder or like not as hot as the metal spoon. Because like when you touch the metal, you'll be like, ow, and everything. But the reason for that is because like metal is a conductor, as we learned in previous lectures. And so that is because like, and also that affects heat capacity, and heat capacity is like energy. So it takes a significantly amount energy, less amount energy to heat a metal spoon up versus a wooden spoon because of the heat capacity. So there's your real life example for today. All right. There's different types of heat capacity that we're going to study today. The first one is just normal heat capacity about, so that is the formula Q equals Cp delta T. And Cp is just like the heat capacity in joules per degree Celsius, and where Q equals the heat and delta T is the change in temperature. And remember, you find that by doing the final temperature minus the initial temperature of the object. And so heat capacity is actually used sorry, is actually used when you want to what's it called? Oh wait, I'm not in. Let's see. Well, let's start over now, shall we? Let's three, two, one. Hi guys, so my name is Hunter Frerichs, and today I will be going over with you today the topic of heat capacity, which is lecture 30 in Chem 105, in case you didn't know, but you already know. Yeah, so let's begin. So what is heat capacity exactly? Heat capacity is defined as the amount of energy needed to raise the temperature of an object by 1 degree Celsius. And so you guys may be wondering, like, what's a real world example of this? So no, a real world example of this could be like if you put a metal spoon versus a wooden spoon out in the sun to heat up and just want to compare the two heats for whatever reason, you could say like, and you go out there for you out there for like 15 minutes and then you compare heat, you'll notice that the metal spoon is significantly hotter than the wooden spoon. And that is because the heat capacity of a metal spoon is actually significantly less than a wooden spoon in the sun, than a wooden spoon, because this is because like heat capacity means that the amount of energy it takes to heat up an energy needs to rate an object by the temperature of 1 degree Celsius. And a metal spoon has 1 degree has a significantly less heat capacity because like it takes a lot less energy to heat it up versus the wooden spoon, which takes a lot more energy to heat up. And also this could be because like as we learned in previous lectures, like making connection, this could be because metal is a conductor, and metal is either a conductor or semiconductor, which is which makes it easier to flow energy through it. So energy and heat are very similarly connected, which means that like it's a lot easier to heat up, and therefore the heat capacity is a lot less. So there's your real world example for today. Types of heat capacity are like that we're going to go over today. So there's a regular heat capacity, which is the equation Q equals Cp delta T. And so C sub P is known as the heat capacity, and that is measured in joules per degree Celsius, where Q equals the heat and like needed to heat up the object, and delta T is the change in temperature, which is, as you guys should know, is final temperature minus the initial temperature of the object. So yeah. And another type of heat we're going to measure is heat capacity. We're going to measure is specific heat, which is Q equals m C sub s delta T. And C sub s is known as the specific heat capacity, which is joules per grams degrees Celsius, and m equals mass in grams. And so what specific heat means is that it means that it is the amount of energy needed to heat up 1 gram of an object, of a substance, versus heat capacity, which is just an object in total. Like you don't really need to know anything about the object, like the weight or anything. And so molar heat capacity is Q equals N C sub P delta T, where C sub P is the heat capacity, which is measured in joules per moles degrees Celsius, and N equals moles. So what molar heat capacity means, like the amount of energy needed to heat up 1 mole of a substance. So yeah. And so next we're going to go into this subject of phase transitions. Like, so you have your water graph, right? And so you have your graph with like a water graph, for example. So you have your solid, then you go back to your liquid. Can't see. Oh, yeah. Okay. I mean, you have your solid, so that heats up and then hits the melting point, and then it transitions to a liquid, and then a liquid, it heats up slowly, and then it turns into a gas, it hits its vaporization point, and then gas turns into an extracritical fluid. If I can write. Cool. And then the gas eventually turns into a supercritical liquid. So yes. So during phase changes, like so phase changes, this flat part right here, these flat parts, and those are known as phase changes or like transitions in phases, because you have no temperature applied, and so you have no temperature. So your y-axis is known as your temperature. So whenever like your object is gaining temperature, and then your x-axis is your pressure. And so during a phase transition, you're not gaining any temperature. The molecules are just, there's a constant pressure applied to them, which turns the molecules and makes them change states and change phases. So yeah. And so like this right here would be your solid to liquid, and this right here would be your liquid to gas. And so yeah, let's continue on now, shall we? Cool. And so this has a connection to endothermic versus exothermic phase changes, because oh, I can't do that. Okay. Your delta H of fusion and vaporization, which is, if I'll remind you of the graph again. So let's redraw the graph. Boom, 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 boom. So your delta H of fusion and your delta H of vaporization, those are your, so this right here, your solid to liquid right here is known as fusion. And then this right here is known as your liquid to gas is known as vaporization. Okay. And then, so those are known as endothermic reactions, which is basically, as we called from before, endothermic means that heat, that means that work is being done on the system. And work and energy are being done on the system, and therefore there's heat being added to it. And so therefore it's gaining heat. And so that is known as an endothermic reaction. And delta H of condensation and freezing, which is also negative, is negative because it's known as exothermic, which means that it is releasing energy as work is being done to the system. So work is being done by the system to the surroundings, and therefore it is releasing heat. And so here you have a little chart here, which just shows you that there's condensation and freezing, which are endothermic, and then melting and evaporation, which are exothermic. So yeah. So how do you calculate the Q for phase changes? Let's clear this real quick. Sorry. How do you calculate the Q for phase change in different phases, for say? So for example, if like you have go from a solid to a gas, or yeah, go from a solid to a liquid, you need to make sure you include the the Q value of the solid, like the temperature rising, and then you need to make sure you include the delta H of melting, as well as, because you can't really have the problem without that. And then you need to have the temperature change from when the temperature of the solid melts and the temperature you want at the liquid. Yeah, for your Q value. So for your actual phase change, you can use the equation N delta H. And so remember, N is your number of moles that you have. So you're gonna find out if it's if it gives you a mass of a substance, you need to find out how many moles is in that mass. So that mass is of that substance. So yeah. And then for staying in the same phase, so you're just raising your temperature, you use your classic mass specific heat times your delta T. And then for calculating your Q for the whole process involving temperature change and phase change, you just add each individual component up. So you have one value for solid for that, plus your value for your delta H, and then N delta H and everything. So there's that for you. And so yeah, let's continue on. Okay, so we actually have a practice problem that I'm going to share with you. So it says you're camping in the winter and want to make 1 cup of hot cocoa using 550 grams of clean snow, which is at 7 degrees Celsius for your water source. How much heat do you need if you want the water to be 87 degrees Celsius when you stir in your cocoa? So for this, and here's some information that you just need. So it gives you your basic Q equation, your delta fusion plus that. So those are all you're gonna need for the equation, because you're obviously just going from a solid, because the melting point of water is actually 0 degrees, as you guys remember, obviously, but it's 0 degrees. So you're starting below starting below the melting point. So you're at a solid, and then you go from a solid to a liquid, which is your N delta H. And then you have your temperature change from 0 to 87 degrees. So you have that. Let me see. Do I have an extra page here? For what? Yeah, I do. Okay. Let's go back. Sorry. All right. Cool. So here you go is so what you're going to start out with is finding your Q value for your solid. So that equals 550 grams. And then you're going to times that by your C sub S of your specific heat of a solid, which is 2.11 joules per grams degree Celsius. So you're going to times that by 2.11 joules per degree Celsius, grams degree Celsius. And then you're going to times that by your delta T. So in this case, it's -7, and your melting point, which is 0. So it'd be delta T, delta change in temperature of 7 degrees. So we're going to do that real quick. So 2.11 times 550 times 7. And that gives you 8,123.5. Sorry, some notifications. 8,123.5 joules. And so your N delta H fusion value, your delta H of fusion for this liquid for your snow to water is going to be, so you're going to find out first how many moles you have. So let's actually erase this. Okay, so you're going to find out how many moles you have. So you have 550 grams of water, and then times that by 18.02 grams per mole of H2O. And then you have 550 divided by 18.02. And so that is 30.52 moles. And so what you do for your delta H of fusion value, and was basically you just write out your delta H of fusion, which is, so you have your number of moles, so that'd be N delta H of fusion. And your N delta H of fusion. So that would be 30.52 times your Q value, your M delta H, your delta H of fusion value, which is 6.01 kilojoules per mole, times 6.01 kilojoules per mole. And so that gives you a grand total of 30.52 times 6.01. That gives you a total of 183.4252 kilojoules. And so next you want to find your last your last heat capacity value of water at a liquid state, which is M specific heat of water, liquid water times delta T. And so that is 550 grams times your specific heat of water value, which is 4.184 joules, grams, degrees Celsius, and then times your delta T, which is 0 to 87 in this case. So you'd have delta T of 87 degrees Celsius. So let's do that real quick. 550 times 4.184 times 87. And so that gives you a total of 204.4 joules. And so this problem in this case wants you to convert everything into kilojoules. So what we're going to do is just move the decimal place 1, 2, 3, 1, 2, 3. And so you have 8.123 kilojoules, 183 kilojoules, and 200 kilojoules. And so you want to do 8.123 plus 200.204 plus 183.4252. And so that gives you a grand total of 391.75 kilojoules of energy needed to, how much heat you need. So that's how much heat you need if you want the water to be 87 degrees Celsius. And so, yeah, there's that for you. Let's sort of clear this. Oh, this was another page, sorry. And so there are actually different scenarios where you can be calculating heat. And so like we discussed earlier, there's just heating of an object, which is Q equals CP delta T, and you're heating, and then you can be heating N moles of a pure substance. So like the substance, you're seeing number of moles of that. So that's Q equals N CP delta T. Or you could be heating like a mass in grams. So that's where like your specific heat comes in. Your molar. So like this right here is your molar heat. and this is your specific heat. And so that is Q equals MC sub S times delta T. And then also there's two more like we kind of discussed in this practice problem, which is Q equals N delta H of fusion. So typically, if you get problems like this on a test or anything, your delta H of fusion should be given to you, unless you have to calculate it, which we'll learn later on in the semester. And then your N, which is your number of moles. And then for vaporizing a liquid at its boiling point, it's Q equals N delta H of vaporization. So yeah, and actually if you want to go backwards, so like a liquid to a solid, freezing, or a gas to a liquid, which is condensation, you'd want to have, you just like put a negative sign in front of it, and that's how you calculate that. So yay. Okay. Well, this didn't clear. So, and actually now we're going to do one last practice problem with this, putting everything together and seeing everything we learned. So to recycle aluminum cans, the aluminum is heated from room temperature, which is 25 degrees Celsius, to its melting point of 660 degrees Celsius. So from there, you already have your two temperatures. So that's your initial, that's your final, and then melted so it can be reshaped. If the heat of fusion for aluminum is 10.79 kilojoules per mole, so that is going to be your delta H of fusion from like a solid to a liquid, as you remember. And the molar heat capacity is 24.2 joules per degree Celsius per mole. How much energy does it take to recycle 1 mole of aluminum? About 2 soda cans. So like I've been going through with this with you, and I've been kind of highlighting the key things that we need from this. So you want to have the molar heat capacity, which is 24.2, and you have 1 mole, right? Because your molar heat capacity is N times your molar heat capacity times your delta T. And so what you want to start with here is your heating up from a solid to the melting point. So that in this case is, so it's just 660 minus 25. So, but first you need your number of moles. So you have Q equals 1 mole times your molar heat capacity, which is 24.2 joules per degrees Celsius per mole. And then times your delta T, which is 660 minus 25 degrees Celsius. So what you want to do is just multiply those together. So 24.2 times 660 minus 25, which is 635. And that would give you a total amount of joules for 15,367 joules of energy. Oh, why did I say, wait, okay, sorry, I meant to say 7, my bad. 7, 15,367 joules. Let me see. Mole, degrees Celsius, degrees Celsius. Yes, okay, joules. And so now that you have that, right, you want your you want to do your phase change. So solid to a liquid, your delta H of fusion. So your N delta H of fusion, which equals 25 degrees Celsius. Oh no, you have your number of moles, so you have 1 mole, right? Times times your delta H of fusion, which is 10.79 kilojoules per mole. And so that just gives you 10.79 kilojoules per mole. And so what you want to do is actually convert the joules into kilojoules, because the problem wants us to convert it. Because whenever you're working with these types of problems, you want to convert into kilojoules. So you can just move the decimal place 3 places over. So that's 15.367 kilojoules. So 15.367. Oh, sorry. Oh my gosh. Plus 10.79. That should give you equals 26.157 kilojoules. And so yeah, that's how you do that problem. And it looks like we're all done. Thank you guys so much for joining me today. And if anything happens at all, like just contact Dr. Mortensen for any of your questions or anything.